schoolstacktc.org, and our Twitter handle is schoolstacktc. I put the talks on the website actually this time, so I haven't got all of the last year's talks up there, but we do have some of the more recent ones beginning in May. Kevin, they're not in order apparently. And then these 5 are the ones that were given last time. And so you click on it, it'll actually take you to the video that's on YouTube. We also have a YouTube channel now.
Nice.
So, audio is not great. That's one reason I set up the speakers to try and help the GoPro pick up audio better. But the video's pretty good though. Anyway. So everybody's talk is linked there, and hopefully by next month I'll have your actual user profile set up, and it'll show who gave the actual talk and link to a pretty picture of you. And if you want to throw that into a resume or whatever, you can do that. Then there's also, by request, I set up a GitHub page for the meetup notes. I only have a couple in there. I need to go back in and put the last year's notes in there. But if you present, you can actually throw your notes in there. So I had a couple people submit. Actually, Sam did not put his notes in there yet. Okay. Casey did. So you can actually see all of Casey's pictures, notes, and his readme file. So he's got a PowerPoint file. So anyway, that's there. You can just import that, do a pull request later. Anyway. So next month, September 5th, it's Rick's birthday, so I might bring him a birthday cake. So if you're here, you can expect that. It might be inappropriately themed, but there will be a cake. September 5th, I've never met Chad, but he'll be talking on trailer. That's Chad. Nice to meet you. So I lied.
You're a liar.
20 minutes ago. All right, well, good to meet you.
Connection made.
It actually worked out that Chad was supposed to talk in August, and then Asher's going back to school, so Chad needed to reschedule too, so it worked out pretty well.
Thanks, Chad.
If you want to give a talk in October, there is space available. I think people ask that Casey give a talk on Git, so I don't know if he wants to do October or not and ask him, but you can still submit a talk and we'll get that in. So today, Asher is actually my intern at P&L. Both Asher and Alex are. They do a lot of good work for me using TensorFlow and doing facial recognition on some of the projects we've got going on. And I asked him to give a talk, and he agreed to it. So with that, I'll kick it over to Asher.
Can you hear me through the microphone at all? Yeah.
So guys, got to just set up to get going here before we get in.
Awesome. Yeah, so like Michael said, I am his intern, and it's been really great working with Michael, and I'm super excited to talk to you guys today about neural networks and facial recognition and how it's being used out at P&L and some of the theory behind it. I'm super excited because math was kind of my first love, and so we'll get into that here. I'm currently going to Whitworth University, getting a BS in math and in computer science. And so that's why neural networks were initially really interesting to me, because it was this really crazy theory and math going on that was applied to computer science and all this hype around it, so it got me really excited. Yeah, so right now I'm doing machine learning projects with Michael, and I'm transitioning on to work remotely during the school year once I leave for school. So I'm staying on getting on. So my plan for today is to really go through the motivation behind neural networks, because a lot of people are really excited about it, but it can be kind of fuzzy why we would ever want to use one in the first place. Then we're going to go through some of the theory and the math behind it, which is what gets me excited. And you guys are probably going to like some of the examples that we have here. And then at the end we'll show the application of facial recognition, and some bonus slides if we have time for that. So yeah. And also guys, please feel free to ask questions, just like interrupt me, shout it out, raise your hand, whatever you want to do. I'd love to just break and answer questions if you guys need that at any point. So don't be afraid to do that. All right. So why would you ever want to use a neural network? So there's some problems that we deal with that computers are really good at, and some problems that computers are awful at. Problems that computers are awful at are called intractable problems, in that they're not very well suited to the von Neumann architecture, which is how computers do things. You guys know all about that. These are often problems that we as humans think are really easy, but computers find extremely difficult. It's extremely hard to get computers to figure out how to do this. For example, computer vision, facial recognition, fuzzy logic, things that have a lot of gray area and need a lot of inference, computers are really bad at. But that's where neural networks come in. So with that, just a high-level overview of what a neural network is. We have some nodes here. You can see the different colors, and I'll explain what those mean here in a second. But the basic idea is we pass data into the network during the training phase, and it returns data to us, and we tell us if that data is correct or not, and then it goes back and makes adjustments. And then at the end of that whole training cycle, we can then feed data through, and it's the data that we would like returned to us. So in this example, this is a network that knows perfectly how to do the XOR operation. And later on, we'll code up a full neural network that can do XOR for us. It's really simple. But this network, you can see, you feed it a 1 and a 0, and it returns a 1. Right? This data on the left side is the data that we feed into the network. That's called the features of the data. And the labels, that's the intended data that we would like to receive from the network. So at the end, when we have a fully trained network, the idea is that you give it the features and it returns the label that it should be. Right? Just super high level understanding of that. And so you notice up here there's these blue nodes. These are not actually nodes in the network, they're just inputs. So when we define our network, you can think of it kind of like these things at the bank that you just put this capsule in and it sucks it up in there. So these blue nodes right here are kind of like these suction things at the bank. So we put our data in and it sucks it in. It doesn't actually do anything, but it's a critical part of the graph, which we'll get into in a minute. So the idea is we bundle up our features into these capsules, and it feeds through the network, and we spit it out, and ideally we get the capsule which has the intended data. So just a little high-level overview before we dig into that. So this is a little bit of history behind how it started. Neural networks are really popular right now. They actually started back in the 1950s with the idea of the perceptron, which we'll get into exactly what that means, but it's just this really simple mathematical operation which takes some inputs and mimics the biological neuron that we have in our brains. And then when you layer a bunch of these perceptrons together, you get a multi-layer perceptron, which is what we call a neural network. So what was a multi-layer perceptron is now called a neural network. They mean the same thing, it's just different nomenclature for that. And the activation function is just a term that you're going to have to be familiar with as we go through this. It's also called the threshold function. There's a few different names for it. But it basically takes some input and squishes it into some interval. And the kind of understanding of an activation function is what helped to advance neural networks, because it made the computations much less expensive, kind of enabled them to work on the hardware that we had at the time. So we'll dig into what all that means here in a second. All right, this is the theory and the mathematics behind it, which is what gets me excited. So this is a neuron in your brain. All right, it takes inputs up there at the left side. There's the dendrites, and all those inputs come together in the middle and shoot down the myelin sheath, which is this tube here. And so as the input comes in, it's summed together and then shoots down the myelin sheath. And if it hits a certain threshold, then it's activated and the signal goes down to the end and is connected to other neurons at the end of that. So in the same way, we define a kind of mathematical operation that mimics that, okay? So all these x's that we have, x1 through 4, those are the inputs that we get into this neuron, okay? And the weights are, so when you have an input, it's multiplied by that weight before it goes into that summation. It's kind of the link between the input and the summation. And then in the end, you sum all of those together, and it's put through that activation function that we talked about. And if it is summed high enough that it triggers the activation function, then it shoots down the myelin sheet. Okay, so we just applied mathematical terms to a biological neuron. And that now allows us to explain it in explicitly mathematical terms. So here, we have the same exact layout that we had before, it's just all the biology is gone. Now we're just talking about a math term. The only major difference that we have here is that one at the very top one that feeds in. It's actually not an input, it's a variable, it's just a constant number instead of an input that's fed through the network. That's called a bias. And if you guys have you guys have ever done anything with regression, you know that you have to add a constant after you give your variable multiplier. It adds a nonlinearity to the function, which we'll get into. But just note that that's something that's slightly different than the biological neuron. And so you can see that each input and bias is multiplied by a weight and then connected to the central part of the neuron where it's all added together. And then it's pushed through that activation and that step function at the very end. And the terms that we'll need to know, don't worry too much if you forget this, but it's helpful to know that that summation part is going to be referred to as Z, so the Z of that neuron. And then after it's put through the activation function, we're going to call it the A of that neuron, the activation of that neuron. So that'll be helpful later on, but it's not critical to know that. All right, so we have this concept of a node, this neuron in the neural network. So when does that actually become a neural network? Well, that happens when we wire a few of them together. So you can see these eyes right here are the inputs that I talked about before. It's like in the bank, the thing that sucks up the little capsules, and it feeds it through the network, and we have N0, 1, and 2. So those are the actual neurons that we talked about before. And so you can see, as we go from left to right, there's connections between one layer's neurons and the next layer's neurons. And so when we apply weights to that, there's a weight between every single connection like we talked about before. So as data flows through, one input is multiplied by the weight that connects it to the next neuron, and then that's all summed together. We have some graphs of that here. Yeah, so when data flows through the network, we're going to get into the actual operations that entails. So, there we go. Yeah, so you can see the red lines up there. As data flows in through those two inputs, the Z of that N0 neuron is going to be the sum of those two inputs multiplied by their respective weights, plus that bias that we talked about before. Okay? So it's kind of just a regression, just a linear regression, if you guys have ever worked with that. And so the Z is computed through summing of the inputs multiplied by the weights and then added to the bias. And then the A is just that Z passed through an activation function. So now with those two inputs, we've then calculated what N0 is. And then if we go here, calculate what N1 is. And this is where it gets a little bit interesting because the outputs of N0 and N1 then become the inputs to N2. So you can see the Z is the output of node 0, which is A0, multiplied by the weight 0, 1, which connects the node 0 and node 2. So you can see kind of the data propagates through this network in this kind of series of functions. If you guys are like me and it's kind of hard to get stuck in all the equations, we'll have some other visualizations to help with that. So just before we move on, just a little quick recap here. We have a neural network, which is a series of neurons, a series of perceptrons all wired together. Data flows in, we compute the value of each node at one layer, we compute the value of each node at the next layer, and propagates through. And then we can compute the output of the whole network. So, you guys all clear on that? All right. Okay, so all we've described so far is this arbitrary way to compute, to push data through some series of functions. It doesn't really do anything exciting. But what we want to do is apply the learning part of this. Because if there's no learning, it's not really stimulating the brain, it doesn't really do anything interesting. So in order to get into that, first all the values, like all the weights and biases that we talked about before, those are all random. So when you push data through, your output's just going to be rubbish, just totally random. It doesn't give us anything. So the way that we have the network learn So we apply what's called back propagation. Yeah, so when we compute this loss function right here, this is one of the last functions that we'll talk about before we get to some more fun stuff. But the way that we determine how well a network is performing is we take the difference of the intended output, which is the label that we talked about before, and the actual output of the network. We subtract those two and square it. So that's our loss function. That says basically how bad is this network doing? How good is it doing? So, and then in order to make corrections on the network, we use that loss function in order to change all those weights in order to increase the accuracy of the model.
Now, is that usually binary, like it's either right or wrong, or on a kind of more finer grained scale of it's 3/4 of the way there?
Yeah, so at each of these values, everything's like a number. So you might feed through something, and so let's say the output, the activation of node 2 is like 0.4, and we want it to be 1. So then the loss would be 0.4 minus 1, 0.6 squared.
It's mathematical.
Yeah, it's just a bunch of functions. It's just computational gravity.
So when you start getting to like, is it a cat kind of thing, sort of thinking it's like,
Yeah.
you know, you can't put a number to a cat. Like, is this a cat? You know, how much you minus from what it gave you, I guess, is one.
Yeah, well, so
You can't do a color. To a color, yeah.
Well, so the way that it's going to work as we get going, I know this will all make sense a little bit more as we get going, but here we just have one output node. At the end, let's say we want to choose between a cat and a dog. We have two output nodes, and the output node that has the highest value is the network's prediction. All right? So if we go through and...
So it would be binary. So yes, it's this, or it's this.
Yeah. So the answer is kind of like a vector. Right, so the intended output, we have two nodes right there. One node could be 0.4 and the other 0.6, which would mean it's predicting the 0.6. And so the first value is cat, second value is dog, then it would be 1, 0. And so you then take the difference and then square it element-wise and then sum all that up. So the mean square error basically becomes the sum of the square errors. So when we get into the TensorFlow implementation of that stuff, we get to see the real numbers. So that might make a little bit more sense, but is that clear up at all?
Yeah.
Okay. All right. So the magic of all this is what makes neural networks so exciting and so interesting. It's called back propagation. So on the last slide, we figured out what our loss is. This is how bad the network is doing. What we're essentially going to do is say, okay, this is how bad the loss is. And then we figure out how much each of those variables contributed to the answer, and then we use our performance, which is the loss, to adjust each one of those variables in order to lower the loss. Okay? So it's a big fancy term, back propagation, but what it means is we work backwards to change all the variables in order to lower the loss, make us more accurate. Okay? So stochastic gradient descent, we'll get into this I think the next slide here. But we have like the surface of loss, and so kind of we're walking down it. Think about it in 3 dimensions. We're trying to get to the bottom of this valley of loss, which would mean we're accurate. So let's take a look at that. So for this example, we just have a parabola, but let's say that this is our loss function. So our y-axis is our loss, and our x-axis is some variable within the network, like a weight 0, 0, or something like that. So if we increase the value of the weight or decrease it, and that corresponds to some increase or decrease in the loss of the function. So let's say when we start our network, our loss is right here, okay? With everything randomly initialized, all the weights are just totally random, our loss is right at that value on the curve. So in order to walk down this curve and make adjustments to everything in order to minimize the loss, what we do is we take the derivative of that point and we see which direction is positive and which direction is negative, and that tells us which direction to walk. It's really simple for us to see in 2 dimensions, but it'll get a little bit crazy. So we see that this direction is the down direction we want to be moving in, so we take a little bit of a step. Right? Then we take the derivative again and say, okay, we want to keep taking another step to the left. Okay, the derivative, another step to the left. Eventually we get down here, which means our loss is 0, which means every output of the network is exactly the intended output, which never really happens with neural networks in the real world, but that's just for this example. You can see that we play with the values of the weights in order to lower the loss. But this would only be if we have one weight that contributes to the network. So what happens if we add another weight? right? Because in our network, we have 8 weights and then a bunch of biases. All these are variables that we have to play with. So you can see that we have this paraboloid, which is our surface now, but instead of just having 1 weight to play with, now we have 2. So we need to say, okay, how do we adjust each weight in each direction in order to walk down to the bottom of this valley? Okay? So let's say we start out here. It's kind of hard to see when I plot it like this with this wireframe. I can figure out how to get a decent plot for you guys. So this over here is a little bit of a better plot. But imagine this z-axis is the loss, and so this x and y are 2 variables in the network, like weight 1 or weight 2. And so you can see if we kind of play with each of the weights, we can walk down this surface to minimize the loss. And eventually we get to either global or local minimum, in which case the network is about as accurate as it thinks it will ever get. We've descended the surface of loss about as far as we can. And that's usually when you stop training the network and say that you have a fully trained model. So you can see that we went from 2 dimensions to 3 dimensions. Well, as your network grows, you have more and more variables in that thing. In our simple network, I think, went in and counted, I think we have 9 variables to play with. So our loss function for our small little network that we just created is a 9-dimensional loss function. So like these surfaces that we're talking about, it's kind of not very realistic, but it's helpful to understand that we're slowly walking down this path of loss. So now that we've got some more visualizations, we're going to apply this to a few more expressions. If you guys can think back to freshman calculus, a little bit of the chain rule would be helpful, but if you don't remember that, then don't be bad, we can still work through it. The main idea from the chain rule is that, especially the second line, when you take the derivative of nested functions, the result is the derivative of the outer function times the derivative of the inner function, and that whole thing propagates out until you reach the variable itself. Okay, so that's about all we need to know from that. The biggest thing is that in our graph, like right here that we talked about, we need to find the change in loss with respect to each variable, so we know just how to change each variable in order to minimize that loss. And so the expression for that is DLDW, or it could be W or it could be B for bias, but this is just the change of the loss with respect to W. Okay? So in our case, dy dx, right? You think about calculus, it's just that derivative. Well, y is loss and x is w, so the LDW is just this line, which we needed to walk down the surface. Okay? So now that we know we need dLDW, to actually do back propagation, the full back propagation algorithm, you have to do dLDW and dLDB for every single variable in the whole network. We're just going to look at a single example just to get a better idea. So if you think back to our loss function, this is the thing that we're going to be taking the derivative of, right? A2 minus O2, all that squared. So we take the derivative of that, it's the derivative of the outer part times the derivative of the inner part. And so A2 depends on, all the other nodes behind it, so we then take the derivative of each of those iteratively until we get all the way down to W00, which is what we want. So we're going to find the derivative loss right here with respect to W00. So in order to do that, this looks like a lot, but if you actually look at it, each of these terms cancels out. So what all these things mean is we find the change in loss with respect to A2, and then in order to get all the way back to W00, we need to find the change in A2 with respect to Z2, see, dA2 dZ2, and then dZ2 dW01, which is Z right here. So it's the derivative of each of those connections, right? So if we need to find the change in L with respect to the change in W, we need to look at all those connections in between to understand exactly how those changes work. And then if we go back far enough, we get to the variable that we need. So if we get back to the variable we need, we can then make adjustments to walk down that slope that we talked about before. So that's the whole name of the game. The game to be played is to minimize loss. But let's just think about conceptually what this delta means for a second. So when we look at dLDW0, we're looking at what a very small change in W is going to do to the loss function. Right? So if we look back at this surface again, what is a tiny change in this axis or in this axis going to do to the loss function? It tells us which direction we need to start stepping in. Okay? So just to recap, neural networks train on input data, it takes data in, and it spits data out, and we tell it how bad it is, and based on that answer, that loss, goes back and changes itself to be better. Okay? Walk down that error surface. Do you have any questions? No? All right, so now we're going to work through an example here. TensorFlow, if you guys don't know, is a library written by Google. It has interfaces for lots of different languages, so it's not just Python, but that's the most popular one, so that's the one we're using. But TensorFlow allows you to write computational graphs, like these neural networks that we've been talking about. It allows you to write them in a way that can be compiled down to C++ or ran in C++, or CUDA, which if you guys don't know is the native language that runs on NVIDIA GPUs. So you can really accelerate these through GPU, which helps a lot with training. Yeah, so TensorFlow workflow is kind of like you create this computational graph in code, and it's created in the C++ runtime. Then when you feed data through the network, it actually runs it in the C++ runtime or in CUDA on a GPU if you decide to do it that way. So since these computations are really expensive, you've got to do a lot of them, it's really helpful to get that performance bonus, which is why TensorFlow is so popular. And then once you train everything, you can run the train network on new data where you get your predictions. Okay? So let's try this out. So we can actually run this in a second here, but we can see our features and our labels, which we talked about at the very beginning. In the very beginning, I fed in 0, 1, and it spit out a 1 like it should. So this is just the training data right here. Each of these pairs corresponds to a label over here. This is the data that we'll be training it on. Just a super simple example. The X underscore and the Y underscore, they're like the entry points. Like you guys remember the bank illustration where it sucks the data up and in? This is like the tube where you put that capsule. So it's not the actual input data, but it's the tube which will end up taking that input data. So the same right here for the label. The X is for the features and the Y is for the label. And so then we construct these weights, which like I said are initially random. This truncated normal thing, we get too cut up on that, it just means random and normally distributed. Same here. Biases are initially 0. They'll be added on through the optimization algorithm as it goes along. And so this right here, we can just step back for a second. I know it's kind of dense, but it's actually not too hard. And this is the entire neural network. This is 4 lines of code, that's it. This up here is like a little bit of boilerplate, but those 4 lines is your entire network. So if we step through this, and you remember the diagrams that we did before, you can see we have the X underscore and the weights. And so all these operations have to be done in C++ runtime through TensorFlow. So that's why you have to use TensorFlow's add function, TensorFlow's multiplication function. But if you look at it, it's just the feature multiplied by the weights plus the bias, and then pass through ReLU, which is just our activation function. Okay? And then for our next layer, we do the same thing. We multiply the last layer's output, which is hidden 1, by weights 2, which is the next layer of weights. And then we add the next layer of biases, and then sigmoid is our given activation function. So those 2 layers. And then our loss, remember how I talked about how you reduce the mean squared loss across all the examples? So that's where this is right here. You take the squared difference, the difference between these 2, multiplied by itself, and then you take the average of that through all of the examples. And that's our loss function, just like we talked about in the equations before. And this train operation, this is where the back propagation happens. So this is gradient descent, which just means it finds the gradient of steepest descent and takes steps in that direction to walk down that loss surface. This 0.01 right here is what's called the learning rate. So we talked about the gradients, which find which direction you walk to walk down, but the learning rate is how far of a step you take. So if you take too far of a step, then you're just going to be walking all over the surface and you'll miss those minimums. If it's too small, you'll probably still get to the global minimum you want, but it'll just take forever. So this is just a good balance of the learning rate. So we've established our backpropagation algorithm, and then we just tell it to minimize the loss right here. And that's it. It's our whole network. So what we can do now is actually train it. I'm actually going to run it for you guys over here. Right. So now that's important. We've got everything established in our network. So this is going to run, remember I said we have to initialize all our variables because it's in the C++ runtime, so it's kind of boilerplate. You can kind of ignore that if you want. And this is going to say, for 10,000 iterations, pass training data through the network, get the loss, and run the backpropagation algorithm. And then we're going to do that whole thing again. These few lines right here just tell us, just intermediate, so every 1,000 iterations tell us how it does. But this right here is the full training. So we take our C++ runtime, which is defined by this session variable, and so we run the training operation, just run that backpropagation algorithm, and then we have our input. Remember like the bank illustration where we have those tubes where we put the data in? This is where we actually feed the data in. So we have X, which is where we feed the features. So we take our features, which is our data, put it in that capsule, put it up in that bank, and sucks it up into the algorithm. And we do the same thing with the labels. So if we run that, we can see that we start with about 0.2 error, and then we get all the way down to 0.01. So that's pretty good. So now down here, what this does is it just starts up another instance of our network and passes data through it, and we can see how it performs right here. So if we pass in a 0 and a 0 to the network, it gives out a very low number, which is what we're looking for. If we pass in a 0 and 1 or a 1 and a 0, it passes in about 0.88 or 0.96, right? Which is very close to 1, which is what we're looking for. And if we pass in another 1 and 1, we get a very low number. So we can see that it's learned XOR effectively. If we take whichever, if we say less than 0.5 is 0, greater than 0.5 is 1, then we can see that it converges exactly with the labels that we intended for it. So, in a few lines of code, it's pretty simple. We created our own neural network, so I think it's pretty fun. Alright, so how does this apply to images? This is where things get a little bit more interesting, because there's a few more steps to this. Because well, in order to illustrate this, we're going to go through just an example problem. It's a little bit more simple than faces. I'll get to faces in the end now. But the big idea is that for this training, for this example, we have a bunch of handwritten digits, and what we want is a network that can take a handwritten digit and tell you the exact integer that it's supposed to be. Okay. Just another simple example for images. If you ever do like a tutorial online or anything about it, this data set, the MNIST data set, is the very first thing you're going to find. But the big idea is we feed in an image to our network, and then it eventually produces the integer corresponding to that image that we as humans can intuitively see. So that's the game that we play. So first thing to understand when we're working with image data, when we have a given image, the computer only sees just a set of values corresponding to how dark it is in each pixel. So this is where it gets really hard for a von Neumann machine, our basic computer, to really understand this problem. It's not something that's intuitive for computers, but it's really intuitive for us. So when we understand how that data is organized in memory, we have a couple approaches. The first one is fully connected. So the network that we just ran through, that's called a fully connected network. Every node in one layer is connected to every node in the next layer. So that's what we made. But another approach is a convolutional neural network. So we're going to get into what that means here in a second. But the first thing to know is that if we were to feed in some digit, we create a node for every single pixel in that image, and then it would propagate through, and we'd run back propagation until it could eventually predict. So now this is when your question comes into play, right? Because instead of just having like some value that's in this range that's predicting this, you can see there's a node for every possible class. So every possible output that it could be, there's a node corresponding to that at the end, and whichever node has the highest activation or the highest value, that's its prediction. So you can see here, I made it darker for a larger number. You can see that it's predicting 8 corresponding to every pixel.
So this is kind of similar to Watson and the Jeopardy games, where it has a 67% assurance that this is the answer out of like 4 answers. If it's like 80-some% on one, it'll choose that. And then if it's all lower and it's not too sure, then it might decide not to answer.
There's some other logic on top of that too, where you use generic if statements to come up, because Watson's a lot more on top of neural networks, but it's something that is pretty critical to it. But yeah, basically there's a bunch of categories that it could possibly fall into, and then it gives its best guess at what it is. But if all of the possible neurons are like at about the same, that's when programming in Watson would say, I just don't have anything for it again. So that makes more sense now? Cool. All right, this actually has a really big problem. Okay, every single pixel in our image corresponds to a network, or a neuron. Okay, so what happens if we have the exact same handwritten digit, but it's just scooted over a couple pixels? Well, all of these pixels perfectly correspond to a all these neurons, perfectly correspond to a given pixel. So if we scoot it over one pixel, that entirely changes the input data for the network. But as far as the image goes, it's still the same to us. Networks should be able to figure that out, right? So that's where convolutional networks come into play. But before we dive into everything the convolutional neural network is, we've got to look at a few more functions first. So how can we adjust our approach for images instead of a fully connected approach? Because we can see how that can easily be thrown off. So these are the three functions we're going to go over just really quick in order to fully understand the convolutional network. First one is flattening, and pooling, and convolution. Pretty straightforward. Flattening is where we take an image or some data set that's a matrix and we convert it to a vector. Okay. So we're going to have some image and just totally flatten it out. It's pretty straightforward. Pooling is where we take, this is max pooling, there's also average pooling and some other strategies. But max pooling, you look at every pixel in a given region, and the pixel with the highest value is carried over to the next layer. So this is a way of like downsampling. Just like if you ever downsample an image or something like that to reduce file size, this is one of the things they use. This is a function that we'll use in our network. And then the last one, this
What
one's
gives that pixel a value?
What's that?
What gives that pixel a value?
So this is like an image. So if you feed in an image, just imagine instead of 4x4, it's 720 by 1080 or something like that. So you take a picture, you take the greatest value, usually RGB.
Okay.
So if a given image isn't just this, it's 3 of these, and each pixel corresponds to the red, green, or blue, or alpha channel of an image. So a single image is usually 3 or 4 of these. So we call it color channel. So it's a way to downsample everything. This is convolution. If you've ever done convolution physics or something like that, I never have. This person I've really used it. But essentially what we have is, on the very left over here, that's our image that we get as input. And then this thing in the middle is called our filter. And we'll go into what that really means. It's kind of like a weight in a fully connected network. But you can see here how each value of this filter is multiplied by the corresponding value over here. So you can see these calculations up here. It starts at the top left pixel, so -1 times 3, -1 times 3, and then it's added to 0 times 0. So it's just applied right there. And then you scoot one pixel over to the right and apply it like that. And so you multiply each area of the picture by that convolutional filter. So it's kind of interesting to get your mind around, and then you see how all of that is summed together to get just one value on this destination panel. And this is what we're going to call the feature maps. There's some really interesting properties with what that gives us here. So the big idea with that is we have these filters which are initially random, just like those weights. And when they're applied to each section of this image, it then produces some sort of convolution of the image. And it's interesting because if this filter has just a straight horizontal line, if you think about it, whenever it's convoluting the part of the image that has a horizontal line, then the corresponding area of the picture on the destination panel or on the feature map is going to be extremely bright. It's going to be a high number because it matches up very highly. The filter matches up very highly with the image. And if it really doesn't match up with the image, then the feature map will be negative in that area. So it basically takes whatever arrangement is on these filters, and then on the feature map shows you where that feature lights up. So there's kind of a lot to unpack there. But there's interesting, dang. So we lost some slides there. I should have some more examples of features, but that's, or filters, that's okay. This is like a set of filters on, I think this was from ResNet, which is a great company that produced that. It's a big neural network that uses convolution. And these are some of the filters that it came out with. So you can see right here, there's like some edge detection. It's kind of looking for horizontal or diagonal lines. That's a horizontal right here. Over here, it starts looking for color, that kind of thing. You can see that these filters are looking for really specific features of the image. And so when we apply back propagation, we apply it, I won't go into all the math of that because it's a little bit more involved, but it adjusts each part of the filter in order to detect really specific parts of images. So you can see the MNIST data set, the handwritten digits, the images are pretty small, but when we blow that up to facial images, it starts to look for interesting things like eye shapes, maybe jawline, hair color, facial hair, that kind of texture, which gives us really interesting things. That's where convolution really gives us its benefit. It kind of abstracts us away from the raw pixel data, which is what made the fully connected network fall short. So when we put all that together, we pass in our image, and through convolution, we get these feature maps. And then through pooling, we shrink those feature maps down, and then apply convolution to the feature maps. And then we pool it down again to make it smaller. And then we take every single one of these feature maps and we flatten it out. And then once we flatten it out, we just have a big long vector of values, which then plugs into a few fully connected layers, just like before. And then at the end, we still have our 10 nodes at the end, corresponding to 0 through 9. But it's fully connected and it's looking at each of these features. So for example, if a given image has a lot of horizontal lines lighting up in a certain area, it might learn that that corresponds to a 9 or a 1 or something like that. So it has an interesting way of looking for parts of images. So that's where it really wins over the fully connected network. And you can see it actually includes the fully connected network in it. It's just the fully connected network learns from the features. So, just to recap there, this convolutional network looks at higher level information rather than just the raw pixel data. If we just look at the raw pixel data, we're going to be thrown off right away if there's just some tiny adjustment. That's not really what we want. We want it to look at a more abstract view of the image. Pooling reduces the number of data points because when you feed in bigger images, you want to classify bigger images, your data can get very, very large, very computationally expensive. So pooling helps us shrink that down and take only the data that's really relevant. And then this is what helps image classification, because it's no longer looking at just the raw pixel data, it's looking at everything convoluted over the whole image. Does you have any questions? Good? Right. So recognizing faces is really hard if you think about it. There's a few things going on past just recognizing an image like we talked about. People's faces change over time. People get facial hair, they wear hats, they wear sunglasses, everything changes about people, but we want a network that can still recognize them through all that. It's also, to think about it, like just really classifying a 2D projection of a 3D surface, which is our face. This is another interesting problem. And also facial expressions. Facial expressions can really change a lot of things about a face, but we still want to recognize it as the same face. We want a network that has a really high abstract view of images, not just looking at raw pixel data. So in order to get that, we have to overcome a few problems. In order to get training data, we have to get pictures that are good and clear of people's faces to train the network on. But we get some interesting problems, because right here's a given face, just cropped at 3 different angles, and you can see there's a lot of dark pixels over here, none over here. The images are actually quite different, even though it's the same face. Now this isn't aligned. If you align it over here, you can see that this image versus this image is actually pretty different. So the network has quite a bit to learn if it wants to be able to tell that this face is the same as this face. So it's a difficult and interesting problem. So the first step in order to solve that is actually a different machine learning algorithm called a Haar cascade. So it's basically sections off on the binary search, I guess you think of it, each part of the image and incrementally searches it, looking for a specific thing. So the Haar cascade is really good for finding things in images, but it can't tell you what the thing is. It just learns to map it out a little bit, give you a bounding box. So you pass an image through one Haar cascade, and then from there you can crop out the image that it finds and pass that through the network, and that gives you a little bit of a bonus. There's another algorithm which lets you align the face, which gives you another little bonus. So these are some problems that we need to overcome. So the workflow of it, when you get everything working together, is you have your image, you pass it through your Haar cascade, and then you take your cropped image and you pass it through your neural network. And then out of that, you hopefully spit out a name. That's really the workflow of how all this comes together. So I'm going to show you guys an example. This actually has, this is actually me and Alex. We took this to use as an example. So you can see we move around a little bit, try and, you can see when the space moves around, it kind of tweaks out, doesn't really know what to think of it. But I am indeed Asher, and this is indeed Alex. So this is kind of the example of the whole heart cascade, cropping faces, resizing, readjusting everything, then passing it through a network. This is kind of the whole story when everything comes together. So that's the whole workflow currently. There's a few more state-of-the-art things going on that are really interesting that we can talk about. If you guys have any more questions or you just like to talk about it a little bit, we can do that, or we can go into some of the more state-of-the-art things. What would you guys like to do? Go through some of the state-of-the-art stuff? Who's interested in that? All right.
State-of-the-art.
Yeah. That's what I'm saying. All right, so this is our convolutional network that we looked at before. If you'll notice, it's kind of linear. This goes to this goes to this. Everything is like a chain. Nothing ever branches off. But one thing that's really interesting that Google came up with is called this inception module. So one thing they do, if you take in an image right here, it passes it through layers of convolution, another layer of convolution, and it adds all those layers back together. So it branches off. There's a bunch of interesting stuff inside of each one of those branches. So if you take a whole ton of those branches and wire them together, you get this big guy right here, which is the Inception version 3 model Google came out with for image recognition. If you guys use Google Photos, it uses a lot of that. If you go to Google Photos and type in mountain, you find all your photos and pull a mountain for you. This is one thing that Google uses that for. There's another interesting model, which is called the dense net, which takes every layer and connects it to the following layer ahead of it. So you can see there's a lot of connections here. So it has some interesting properties in that. So down here, there's some filtering going on, some convolution. So you have really low-level features like textures and that kind of thing. And through many more layers of convolution, all the way up here, you get really high-level things like eye shapes and contours and that kind of thing. But when you add them all together at every step, each part of the network is looking at both high-level and low-level features in an interesting way. So that'll maybe be able to combine different elements like that. This is actually a research question that I'm kind of investigating right now at PNNL, where I have inception modules like this, but they're densely connected to each of the following layers ahead of it. So this has the interesting property that right here we'll get different levels of features like texture, contour, color, that kind of thing. But then this is also added to the network at the very end. So right up here, when we're trying to classify faces, we can look at things like texture, eye color, eye shape, really high level and really low level features all at the same time. It's something I'm investigating currently right now in and out of my internship over there. So, yeah, and with that, if you guys want to contact me, have any more questions, I'll put the slides up on the website, but it's that. Thank you guys so much.